Hello and welcome, guys. This is my fourth lecture on chapter number 9. So, so far we have been discussing annuities and assurances where the order of death of two lives is important. Okay, so we cared about which life died first and which life died second, and basically on that basis we paid assurances or annuities, right? But now we will be dealing with a topic called as more complex conditions. Okay, so we would be dealing with some new kinds of annuities where more complicated conditions would be imposed on the payments. Okay, and we would have to find out their expected present values. Okay, so this topic is given as more complex conditions by this name in the core reading as well, so you can refer to it there. So let's start talking about it. So all the annuities that we would be dealing with here, all the cases we'll be dealing with, we would be assuming one thing. Okay, the thing we would be assuming is that payments are made continuously. Okay, so we would be dealing with all these annuities where the payments are made continuously, and this gives us a direct consequence. Okay, this implies that we would be able to use the integrals since the lifetime and the payments, everything becomes a continuous random variable in this case. So we won't be we won't need to deal with discrete times of payments. We would be assuming that the payments are made continuously, and in order to sum them we will be using integrals. Okay, so that's the advantage. And when we get questions where we have payments which are made in advance or in arrears, we will what we'll do is we will actually use the continuous versions of these annuities. We will be um, transforming everything to the continuous version. We would be assuming that initially that the payments are made continuously, so you assume this, and this would be used to simplify the formula. So we will use these integrals to get a simplified formula, and once we have this simplified formula, we would be then transforming the simplified formula into annuities which are payable in advance or in arrears, and then getting our solution, right? So initially we would assume continuous payments, and we would be solving integrals in order to get a simplified formula, and then using we would apply that simplified formula to advance or arrears counterparts. Okay, so we'll see when we get there. Okay, I would be discussing more of this when we discuss the revision notes, but this is something you should know, that we would be firstly assuming everything to be continuous, and then we can actually apply the same thing to advance and arrears, right? So that's something very interesting. Okay, so let's discuss this. Let's start by discussing the example which is given on page number 19. Okay, so this question says that find an expression for the probability that Xanthia, who's aged X, okay, Xanthia, who's aged X, will die more than 5 years after the death of her sister Yolanda. So we have got two sisters. One is called Yolanda, and the other one is called Xanthia. Okay, and they are both aged X and Y respectively, right? And what I want is I want Xanthia to die 5 years after Yolanda. So they are at inception, they are aged X and Y, and I somehow want that whenever this Yolanda dies, Xanthia has to live for basically 5 years more than her. So maybe the time of death of Y can be called as T, right? That is the critical event here that we have to model. So the lifetime of Y, if it is equal to T, the lifetime of x, okay, has to be greater than t plus 5, right? That is what I want here, right? So that makes sense. So express this answer in terms of a single life, in some terms of single life probabilities based on the first death, right? So we have to base this on the first death, that is we have to base it on the death of Yolanda. And what I want is for her to die, and I want Xanthia's death to be more than 5 years later than this. That is, I want her to be at least be alive after 5 years of death of Yolanda, right? So she has to live for at least 5 years after the death, and then she can die whenever she wants, right? I mean, not under her control, but yeah, I won't care about it. Cool. Okay. So what is this probability? So this probability is equal to going from 0 to infinity, right? We are trying to model the critical event, that is the death of Yolanda. So I want Yolanda to die at a certain arbitrary time t, right? And I want Xanthia's death to be more than 5 years after that. Okay, so let's think about it. So what happens is Yolanda dies. Yolanda has to live for t years, that is tpy, and then die immediately, that is mu y plus t, right? And dt, of course. Okay. And I want Xanthia to be alive even 5 years after this. Okay, so Xanthia, that is X, has to be alive 5 years after this. That is, has to be alive till t plus 5, right? So that's your expression for this probability. I don't care about the death of X. I just care about that she is alive 5 years after the death of Y, right? So that's my expression. Now I have to express this in terms of single life probabilities. So what I can do here is, see, now throughout this section of this chapter, you will learn a few techniques of simplifying these integrals. And this is the first technique that I'm teaching to you. Okay. The technique is that I can somehow actually take a constant out of this thing. There is a way to get a constant out of this thing. The way is that I can actually write this t plus 5px as, I can write it as 5px, which would be a constant with respect to t, into x plus 5 tpx plus 5, right? So I can write this in the form of this, right? So that's something you can do. Okay, and I already have this going from 0 to infinity tpy mu x plus t and dt. So this is one way of taking a constant out. So this term is a constant now. So I can take it out. So it becomes 5px, and this going from 0 to infinity tpy into mu x plus. Okay, let's simplify this. If I multiply this these two expressions, tpx and uh, tpy and tpx plus 5, so this becomes tpx plus 5 and y, right? So this becomes a joint life probability because they can just be multiplied into mu x plus t, mu y plus t, sorry. Okay, there's a mistake here. Let's fix this using an eraser like we used to do when we were kids. This becomes mu y plus t, right? And this also becomes mu y plus t dt, right? So this is what I have, right? So what does this mean? This means that I want y. Okay, let's just try to understand this integral here. Okay, this just means that I want y to die from any time between 0 to infinity. Okay, and I want x plus 5 to be alive at that time, right? So that is what it means, a life aged x plus 5 and a life aged y, and y has to live for t years and then die immediately, and x plus 5 has to be alive then, because there is no mu x plus t here, right? So you should get that, right? So this is basically, if you go back a few pages and you compare, if you want to, this is the expression for uh, we used to have something, if there was an n here instead of infinity, We used to call this as nq uh, x plus 5 y with a 1 over y. We used to say that we are modeling the death of y. So first of all, we check basically the status with the number over it, so that is y. So we have got 1 over y, so we want y to die first within n years, and then we want x plus 5 to be alive at this time. So that is what we are modeling here, right? That is what how we used to deal with it. So this can be written in this way, that I want y to die and I want x plus 5 to be alive, right? So that is how you can model it. Now that we don't have n here, we have got infinity here, so n is equal to basically infinity. So we'll write this as 5px into infinity q x plus 5 into y1, right? So that's the way to model such a probability, and this is your answer. Okay, so that's how we go about solving this. So that was one way of solving this question. Actually, there can be another way of doing it. Okay, so I'm trying to show you the other way to see. So the first death here was of y. Obviously, we wanted y to die first, and then that is Yolanda to die first, and then I wanted x to die 5 years after her, right? So what is happening here? If we try to model this on the based on the death of x, okay, we can also do this. So the condition would be that I want x to die at a certain time t, and if x dies at time t, I want if I want the same condition to happen, I want y to have been dead 5 years before t itself. So I want y to die before t minus 5, right? So y has to be dead by t minus 5. So this is another way we can actually solve this question, because the condition they had given us was that we want the probability that x dies at least 5 years after x dies um, more than 5 years after y. So we can also see it as that y dies more than 5 years before x. Okay, so that is what we can actually do, right? So this is how we can actually model this in another way. So let's try to do it. Okay, so I'm talking about the death of x first, that is my critical event. So from 0 to infinity, this t, that is the critical event, can occur, and this event is x lives for t years, that is probability that life aged x lives for t years and dies immediately. So mu x plus t into dt, of course, in a short period of time dt, x has to die, and y should have already been dead for more than 5 years. So y should have died by t minus 5. So this becomes t minus 5 qy, right? So that's how you can model it. So now let's just simplify this. In order to simplify this, what we can do is we'll need to convert the q probability into a p probability. So let's do that. So this becomes going from 0 to infinity tpx into mu x plus t into 1 minus t minus 5 py, right, dt. The reason we did this was that we do not actually have any definition as such when there are q probability there. So we can only simplify them because it's only possible to divide this kind of probabilities t plus s x kind of px kind of probabilities into tpx, and then we can call it px plus ts, right? So we can divide these this way, but we cannot divide the q probabilities. So this is why the first thing is that we have to do is, in order to take out the constant the way I did in the previous case, the previous form of the answer, I need to actually have p probabilities here. Okay, now going from 0 to infinity, I'll have a tpx into mu x plus t. Okay, minus going from 0 to infinity, I'll have a tpx into mu x plus t. Of course there's a dt here, okay, and there's a dt here, and I'll have a t minus 5py, right? So that is what I do. Now this part can actually be, if you observe it very carefully, this is the probability that x dies in an infinite period of time. So this becomes infinite qx, right? So that is what it becomes, and this probability, obviously infinite qx becomes 1, because I want x to die at some point of time. That's just 1. Okay. Minus this part, if you check it out, it is, so in order to solve this, we actually need to do a substitution. Okay, since we have got this t minus 5 here, this is a bit complicated kind of a thing, and we cannot even divide this p into two parts. So what we'll do is we'll do a substitution, that instead of t minus 5, I'll put s. Okay, so that's the substitution I'm doing. Okay, so this implies that dt would be equal to ds, right? So that does not changes. Okay, cool. So what would this become? The limits would change now. Since t minus 5 is equal to s, so we had t here. Okay guys, so there is a bit of an error here. Okay, the error is that instead of this 0, I'll have a 5 here. The lower limit of this integral would be 5 everywhere. And the reason for this is that since see, what I want is, I want x to die at time t, and I want y to have been dead at 5 years before t, right? So the minimum value that t can take has to be 5 years for y to have been dead at time 0, right? Otherwise y's death won't even exist. The time of y's death won't exist, so the entire integral would become meaningless. So I don't have a 5 here. Instead of this 5, I have a I don't have a 0 here. Instead of this 0, I've got a 5. Okay, so let's change this everywhere. Okay, cool, right? So this is what I have, right? And the probability of this person dying between time 5 and infinity is also, so since I've got a 5 here now, I cannot write this as this qx infinity, because I don't have a 0 anymore. So this entire thing changes too. So what I need to do now is I need to apply the same substitution into both of these parts, right? Sorry for the confusion. Let's just apply the same substitution here as well. Okay, so a good thing we realized out of this is that we have to see where t is starting if we are imposing a certain condition before it to happen, right? So we have to make the substitution in both of these parts. Okay, so now t minus 5 is equal to s, right? So when t was 5, s would be equal to 0, right? When here we were setting the limits for t. Okay, when t is equal to 5, s is equal to 0, right? And when t is equal to infinity, s is also equal to infinity minus 5 is still infinity, right? Infinity is so large, you deduct anything, it stays infinity. So it goes from 0 to infinity. Now this becomes tpx. Instead of tpx, what I will have is uh, it would become, instead of t, I'll have, since t minus 5 is equals to s, so t is equal to s plus 5, right? So this becomes s plus 5 px, right? And mu x plus t dt. No, instead of dt now, sorry, instead of all the t's, I'll have to put s plus 5. So this becomes x plus s plus 5, right? And ds. So that's what I have. Cool. And now minus, going from 0 to infinity again, because when t is 5, s is 0, and the same thing, right? Tpx again becomes s plus 5 px, right? And mu x plus s plus 5, okay? And t minus 5 is s, so that becomes spy, right? So this is what I have now, and obviously a ds here, right? So that's how these integrals actually change. Now let's just see what we can do here. See, we have got this s plus 5px here and s plus 5px here as well. So instead of this s plus 5px, what we can do is we can divide it into two parts. Okay, the two parts would be x lives for 5 years and then probability that x plus 5 lives for s years. So that is what I will have. Okay, I am dividing it into two parts. I want first x to live for 5 years and then I want x plus s to live for x plus 5 to live for another s years. So that would total up to x living for s plus 5 years, right? And I would have a 0 to infinity obviously, and mu x plus s plus 5 and s by ds, right? And here if you check it out, it becomes 0 to infinity. Again the same thing, instead of this becomes sp 5px into spx plus 5 mu x plus s plus 5, and that is what I have. Okay, and ds of course. So now I can like before, I can take the constant out. So the constant is s, obviously 5px, it is 5px. So 5px is taken out of both of these. This becomes 0 to infinity spx plus 5 mu x plus s plus 5 ds, minus going from 0 to infinity. This part is gone and this becomes s plus x plus 5 mu x plus s plus 5 into spy ds. ds, right? So this is what I have now. What this changes to is this becomes 5px, that is a constant. This term can be written as the probability that a life aged x plus 5 dies infinitely at some point of time, right? So this becomes infinite qx plus 5. So that becomes 1, right? So this can be written as 1 minus this term. If you look at it, this is the probability that um, the life aged x plus 5 lives for s years and then dies immediately, and y is alive at this time. So this can be written as q. Okay, y is alive at this time, so y has to be alive and x plus 5 has to be the first death. So that becomes q x plus 5 y with a 1 over x plus 5, right? We'll have a 1 over x plus 5, and this happens in infinite years. So this is your answer for this entire thing. So this becomes spx 5px, sorry, 1 minus infinite q x plus 5 with a 1 over it and y. So this is what I'm trying to calculate here, and this is my answer. So this is another way of solving this question. And okay, so very similar to this previous example, we have the next example. Let's look at this. This is Xanthia wishes to take an assurance of 50,000 payable immediately, right? So the sister Xanthia is trying to take a assurance contract. It's not an annuity, it's an assurance contract payable, which is of 50,000 payable immediately on her death. Okay, under the conditions described above. Okay, so the condition is that Xanthia has to die 5 years after Yolanda. Okay, so if Yolanda's time of death is T, Xanthia should be alive at time T plus 5, right? And that after this time, when she dies, okay, X dies, whenever she dies, provided that there is a gap of more than T plus, more than 5 years between their death, whenever she dies, she gets an amount of 50,000 pounds, right? So that is the condition that she's imposing here. Find an expression in terms of single life assurances and assurance is payable on the first death for the present value of this benefit, right? So we have to calculate the present value of this benefit, and we have to find an expression in order to get this. Okay, so now they have mentioned it specifically that the payment is made immediately on death, but even if it was not, we would have found out the expression based on assuming that the payments are made immediately, so that we can solve the thing using integrals, and then we would have found out the expression, and then we would have converted it to payments which were payable at the end of the year of death, right? So we can basically do that whenever there is some sort of question like this. You should always start with payments which are made assuming that the payments are made immediately on death, and then you can actually transform the expression into payments being made at the end of the year of death if it is so asked in the question. But in this question it is specifically mentioned that the payments are immediately on death, so that is not a problem here. Okay, so let's try to look at this situation, right? So, see, Xanthia has to die at some time, and Yolanda has to have been dead for more than 5 years before. Okay, 5+ years, right? So what's happening here is the payment is being made at Xanthia's death. So the payment is here, right, and not here. So we have to model the critical event that of Xanthia's death and not of Yolanda's death. The reason for that is the payment is made here, right? So whenever the payment is made, we have to model that particular as time t, right? And this can be modeled as t minus 5, right? That is how we will have to do it. If we model this as time t and this is t plus 5, we won't be able to deal with the payment involved here. So we will be assuming the second way, or the second method of solution that we had done in the last part. Let's just look at this way. Okay, so we are modeling the time of death of x because the payment is made at x's death, right? So how will you model it? Okay, let's look at this. So the amount EPV would be equal to 50,000 pounds into, going from 0 to infinity. What do we want? We want x to die at a certain time. Okay, so we want x to survive till time t. So life aged x survives till time t and then dies immediately, mu x plus t, right? And then I want y to have been dead for more than 5 years. So I want t minus 5 qy, right? That it would have she would have been dead for 5 years. And when this happens, I make a payment of 50,000 pounds, and that is discounted by a factor vt, obviously. So dt is multiplied with this. So this is my condition. This is what I have here. Okay. So let's just try to calculate the value of this expression first. I'm calculating the value of this expression, trying to simplify it. Going from 0 to infinity, I've got tpx into mu x plus t into vt into t minus 5 qy dt, right? This is what I have. Okay. Now, in order to simplify this, like we did in the last question, we will have to write this q as 1 minus p. So this becomes, going from 0 to infinity, tpx into mu x plus t into vt into 1 minus t minus 5 py, right? So I just converted the q probability into the p probability because I cannot deal with q probability that easily. Okay. Now I'm sorry again. This would be from 5 to infinity because the minimum time for the death of x would be 5, because x has to, if x dies before time 5, then we would then y's death would have been in a negative time, which is not possible, right? So it would be from 5. Okay, so that's something we know. So from 5 to infinity, so this becomes, going from 5 to infinity. If I separate this becomes tpx into mu x plus t vt dt, okay, and minus going from 5 to infinity tpx into mu x plus t into vt into t minus 5 py, okay, and dt, right? So these are the two expressions that I have. Now what we do, like we did in the last question, we'll have to substitute t minus 5 as s, because this is a very complicated kind of a thing and we have got a limit from 5 which is unacceptable, right? So for that reason we'll have to write s is equal to t minus 5, or you can write this as t is equals to s plus 5, right? That's something you can do. So this would imply that if I differentiate on both sides, on both sides, ds would be equal to dt, right? So that stands. Cool. Okay. So this becomes going from now the limit will change. Instead of 5 we'll have a 0 and to infinity. Okay. tpx. Okay. Instead of tpx, what will you have? See. T would be replaced by s plus 5. So this becomes s plus 5 px. Okay. And mu x plus t becomes mu x plus s plus 5. So I'm replacing all the t's with s. V to the power of s plus 5, and this becomes ds, obviously. Minus going from 0 to infinity now. Um, tpx would become tpx plus 5. Okay. Mu x plus s plus 5, v to the power of s plus 5, and this becomes spy dy, right? So this is almost solved now. Let's just see what's happening here. See, out of this I can actually divide s plus 5 py px into probability that I have to take out the constant, so probability that x lives for 5 years into probability that x plus 5 lives for s years, right? So that is how you can actually do this. So this gets separated and I get 5px can come out, 5px will come out, and also this constant term v to the power of 5 will also come out. So v to the power of 5 will also come out. Going from 0 to infinity, what will I be left with? I'll be left with spx plus 5, right, instead of x now, because that's how it gets separated, and this part I've already taken out, so this is what remains. Mu x plus s plus 5 remains as it is, v to the power of s, because 5 is gone, ds. Okay, let's take everything in a bracket. Okay, so for this part also actually I can get the same thing out. 5px comes out, right, out of this, so this becomes this, right? And out of this v to the power of s plus 5 also I can take the v to the power of 5 out, right? So this becomes going from 0 to infinity. This becomes oh, there is a mistake here. Right. So this was 5 plus 5 plus s, right? So out of this this part comes out and I'm left with this, so this becomes spx plus 5 mu x plus s plus 5 and v to the power of s plus 5, so I'm just left with a s, okay, and spy, so spy will remain an spy, right? So this entire thing comes in a bracket, and this part I've already right, everything else I've already taken common and out. Okay, so this is the entire expression that I have. Now let's just try to look at it, give single expression for these things. So So 5px b to the power of 5 inside what to have going from 0 to infinity x plus s p x plus s mu x plus s plus 5 and right v to the power of s ds. So this expression is just the probability that I'm just saying that x plus a life aged x plus s x plus 5 lives for s years, right? And then he dies immediately. Mu x plus s is separate. Um, sorry, x plus 5 is separate and s is separate. Let's write it that way. So this was x plus 5 plus s. That's how you can also see it, right? So this life aged x plus 5 lives for s years, then dies immediately at time x plus s plus 5, and then a payment is made obviously of £1, and that is discounted back till time 0 with the factor of vs, and this s can take values from 0 to infinity. So obviously you guessed it right, this is a immediate x plus 5, right? It's just the um, present value of a whole life annuity, that whole life assurance contract that is issued to a life aged x plus 5. You can go back and compare it to a immediate x, which is just going from 0 to infinity, um, s p x mu s plus x v to the power of s, right? So now I just have x plus 5 instead of x, right? So this is the same thing, right? Minus going from 0 to infinity again. This function, what does it become? It's just saying that I want a life aged x plus 5 to live for s years and then die immediately. And at this moment, a life aged y should be still be alive, right? This life is dying from at time s, and this life should be alive, and then and only then I would be making a payment which would be discounted back till time 0 using this factor, right? So this s can go from 0 to infinity. So this is just a immediate. Now what is happening here is y has to be alive. So this is a payment of £1, EPV of a payment of £1 that is made on the death of x if x's death is the first one to occur, because y has to be alive. So this just becomes, and x is obviously x plus 5, right? Aged x plus 5. So x plus 5 1 and y, and that's how you can actually write this, right? So that's how you can express this. This is your expected present value. And if you want, since there was a 50,000 multiplied with it in the beginning, since the amount was 50,000, so this is 50,000 into spx into v to the power of 5 into a immediate x plus 5 minus a immediate x plus 5 into, that's what I have, right? And if this contract wasn't a contract which was payable immediately on death of these people, this can be changed. If it is paid at the end of the year of death, so it becomes 5px b to the power of 5 a x plus 5 minus a x plus 5 y, right? So this is how you can actually change this thing too, right? So there is no issue about that. Okay, so in the last part we talked about a contingent assurance with a complicated condition imposed. Now we would be dealing with reversionary annuities where such complicated conditions would be imposed. Okay, and by complicated conditions I mean that basically so far we had reversionary annuities which had EPV like a due x given y, that is these were the EPV of the reversionary annuities that were payable between the death of x and the death of y, right? So here we had some payments which were occurring maybe either continuously or at the beginning of the year or end of the year or whatever the condition was. Now what I'll do is I'll impose a certain term on this. Okay, so they would be affected by term or a time bound condition. So they have given various types of such conditions which can be imposed, although this is not an exhaustive list and more can be created. But what I want you to understand is the basic idea behind this. What I want you to understand is the basic idea behind this and how do we construct the formula for these things. Okay, so you will be able to extend that logic to infinite number of these types of annuities. So I'm starting with these types. So we have got type 1 here, which is a really simple kind of a contract. Okay, so type 1 constitutes an annuity which is dependent upon failing of a fixed time bound status. Okay, so basically it says that a reversionary annuity in which the counter or failing status is a fixed term of n years. So I want n years to expire before the annuity starts, right? So I want n years to fail. Okay, so I would basically be paying this person an amount continuously because I'm assuming the continuous type of contracts here. You can extend the same logic to the annuities which are payable in advance as well as in arrears. So basically there is a fixed term, and after this term expires there would be payments to payments under this annuity. Okay, so the failing status is this n years. Okay, and consequentially this means that this is just a deferred annuity and nothing else. So there are various ways you can actually write this. See, for the very simple annuity we had, uh, for the very simple reversionary annuity that we had, we used to write it as x given y, that is payment started as soon as x died and they continued till the death of y, right? Now we change it, we want n years to expire, so that becomes a given n, we put it in a bracket because this is time, so we need to show that, and given y, right? So what I want is I want these payments to start after the failing of n years, right? And then I want them to go till the death of y. So this is the same as a deferred annuity. And other ways you can write this is obviously n deferred a continuous y, and the way you calculate this is basically very simple. You can actually take a whole life annuity y, and then you can subtract from it the term annuity which lasts for n years. So I just deduct the EPV of the term or the temporary annuity, so that becomes the y bound by n, right? This is one way you can calculate it, and the other obviously easier way is that we need to take the present value of this annuity till here. So that would become the age of this person was y at this time, right? So it would have been y plus n by this time, so it becomes a continuous y plus n, right? And I just discount it back to time 0, so that becomes npy, the probability that y lives for n years, into vn, right? So this is the simple formula that we used to apply in case of deferred annuities, deferred whole life annuities as well. So this is the same formula that you can use. Okay, so that's just type 1. That's a very simple contract where you just want n years to expire. So before starting with type 2, I want you to remember something that we had learnt about simple reversionary annuities. Okay, so in case of reversionary annuities, what we had was, see, what we used to do was we were at time 0 where we had two lives x and y, and I wanted, I would be paying amounts continuously from the death of x, okay, to the death of y. Okay, so these continuous amounts would be paid in form of an annuity from the death of x. So x dies, and all this while y is alive. Okay, and then I wanted to pay this amount till y dies, right? So that was the condition, and there was the way to express the EPV of this contract were two. Okay, so we had two ways of expressing the EPV. We used to write the EPV as a x given y, and this could be shown in the integral notation in two ways. Okay, going from 0 to infinity, the first way was going from 0 to infinity, probability that we used to model this time t of the death of x, right? That was the first way, modeling this time t of the death of x. So what we wanted was, we wanted probability that x survives till t and then dies immediately, mu x plus t. And then what we wanted was, we wanted y to be alive at this time t, so tpy. And then if y is alive at this time and x is dead, we used to pay a continuous annuity, that is a continuous y plus t, because y would have been of y plus t years of age by now, and this payment needed to be discounted back till time 0 with a factor of vt and multiplied with dt. This was one way of expressing this integral and modeling this condition. The other way of modeling this condition was basically adding up all these individual times. Okay, modeling all these individual times as t. So what we used to do was, we used to model these individual conditions when the payments were occurring. So what we used to say was, as long as x is dead, so at all these points of time x is dead, so we used to write tqx, and as long as y is alive, so both of these conditions should be satisfied, so tpy, right? As long as both of these conditions are operating, we would be paying an amount of £1, right? And that would be discounted back till from each of these times till time 0, right? So a factor of vt and dt, right? That is how we used to model it, and this t can take values from 0 to infinity, and we only used to take that portion of this value, these values, where both of these conditions were satisfied, that y is alive and x is dead. Okay, so we used to model both of these conditions together, and then we used to say this is the stream of payment that we are modeling. So these two conditions can be shown to be equal, right? And these two are the same. And in all the further cases that we would be dealing with, we would be using either one of the definitions, right? So it's up to you which definition you find suitable to use, right? And it would depend from condition to condition. Okay. So that's something I wanted you to, note here. Okay, let's move on to type 2 now. So what do we have in type 2? See, type 2 says, okay, looking at type 2 says, if a reversionary annuity ceases in any event after n years, that is, it is payable to y after the death of x, with no payment being made after n years. Okay, so there is no payment which is made after n years. The expected present value can be expressed as they have given a definition. Okay, so let's see what this is saying. This is saying that what I want is, I want x to die. Okay, and I as long as after the death of x, y is surviving, so y is surviving here, I want to make payments, okay, till the death of y dies here, so I will be making payments in this entire area, but there would be no payment made after time n. So no payment after n years. So what happens is, in order to analyze this, I want you to see this very carefully. See, now n is a fixed time, okay? It is not dependent upon the death of x or the death of y, right? They are saying that after a certain time n, there would be no payment. So if this is the time of death of x and this is the time of death of y, right? If n occurs here, n is here, okay, this is n, let's say let's call this n1. N can take this value which even occurs before the death of x, n can take this value n2, okay, and n can take this value n3, right? So let's say if n takes these three respective values, what would be the impact on the EPV of this contract. Okay, if n is equal to n1, then x is dying here and y is dying here. Thus x is dying at a time that is greater than n1. So the death of x is after n1, right? So basically they have simply stated that there would be no payment after time n, right? So in case n is equal to n1, EPV would be equal to 0 because there would have been no payment, because x and y both are alive here, so I cannot make any payment. Since n dies here, n1 ends here, I cannot make any payment, right? So that makes sense. So EPV would be equal to 0, right? That's one condition. Okay, if n is equal to n2, if I consider this case here, see, then when will be the payments made? Payments would start at the death of x as long as y is alive, right? So y is alive here, okay, and they will keep on going till time n. Okay, so n, okay, we have to stop here. So the payments would be made between the death of x and the expiry of n2 years. So we will have to discount all these payments back till time 0, right? That's how you will evaluate this. Now there can be a third condition, that n is equal to n3. Okay, if n is equal to n3, then we will start making payments. The annuity would start when x dies, and they will keep on going till the death of y, and they stop here. Since n3 occurs after the death of y, we don't care about it, right? It is not restricting our payments. They're going from the death of x to the death of y. In this case, EPV would be same as what it would have been in case ax given y, because n3 is occurring after the death of y. So we have to model all these events, right? And it would get really complicated. So let's see how we deal with this. Okay, so if, see, I told you that I have two definitions for these kinds of contracts, right? So either I can use this definition or I can use this definition. But the problem with using the first definition is that if I model t, that is the time of death of x with respect to n, if I model this time with respect to n, okay, then I would have to model it in three conditions. I would have to model it when n is equal to n1, some time between 0 and the death of x, and then I'll have to model with n2 and n3. That would become really complicated. So what I do instead is that I use the second definition, that is this definition. This is what I will be using. And the reason I would be using this is that this actually models every instant of payment. Okay, t here actually was every instant of payment. See, when I had used this definition, I had told you that I'm valuing every instant where x is alive and y is dead as t, right? So instant of payment is modeled here, right? So I can flexibly use this definition and extend it to this argument, right? So what I do is, instead, I'm using the second definition. So now EPV would be equal to going from 0 to n, right? What? Let's just take it back a second. Okay. So EPV would be equal to something. What is it equal to? Since we have decided to use the second definition, what I'm saying is that these payments, each point is called as t, right? Each of these points are values of t, valued values of t. So t is modeled as when x is alive, all these moments when x is alive, so tpx, so x is alive at t, and y is dead. Okay, I'm sorry, x is dead at t and y is alive at t. So t are all these points where x is dead, so tqx, okay, and y is alive, so tpy. Okay, so I'm valuing all these points where x is dead and y is alive, and the maximum value that t can take now is n. Okay, now the maximum value that t can take is n. T is limited by the term n, because if n occurs here, then there would be no condition here when x is dead and y is alive. See, we have got no condition here. So if I model t as here, I would get EPV equal to 0. Simply speaking, it would be 0, right? Whereas if n would have occurred here, I would have gotten t from here to here, because all these cases, in under all these cases, x is dead and y is alive. So my conditions are satisfied, and they would be restricted by n here. So I am just restricting it by n, right? And if n was somewhere here, then I would have taken in account all these conditions, right? So these all these conditions would have been taken into account. So I'm modeling it when x is dead and y is alive and t is restricted by n, and obviously, so there is a payment made at each of these instant of a unit amount, and in order to discount it back till time 0, I will have to multiply with the factor Vt. Okay, so each of these instant is added with the integral from 0 to n, and then discounted back till time 0 with Vt, and then I have to multiply dt, right? So this becomes going from 0 to n tqx into tpy into Vt into dt. Okay, see, I could have just made you cram the formula and that would have been a whole lot easier. But there are so many conditions that you cannot cram the formula here. The thing is that you will have to understand the logic of how things work. Okay, so let's go step by step about how I thought about this formula. See, I cannot model it using the first formula because I would have to take into account three conditions here. So what I did was I used the second formula. Okay, and in the second formula, I only want those values where all these conditions are satisfied. For t, I want all these conditions to be satisfied. When I'll be making the payments. The payments would only be made when X is dead, because the payments are made after the death of X. Okay, Y is alive, and this T is to be less than N. So all these three conditions need to be satisfied. So I applied all of these conditions. So I discounted it with a factor of Vt and I multiplied with a dt. Okay, so that's how you model these payments. Now let's just once you have this integral, rest of the thing is very easy, going from 0 to n v to the power of t tpy into tqx into dt, right? So now everything is really easy, going from 0 to n vt. Okay, now tpy is here, yes. tqx, now I cannot model it easily in form of q's. I have already told you this. So in order to simplify this, I'll have to take a p. So 1 minus tpx is what I take, right? dt. Now let's just go from 0 to n v to the power of t tpy minus going from 0 to n into v to the power of t into tpy into tpx into dt, right? That's what you have. So now this becomes really simple. This is the definition of an annuity that is payable continuously from time 0 to time n, and as long as y is alive. So this becomes a continuous y limited by n. So this is a temporary annuity on contingent on the death of y. Minus, this is a joint life annuity that is limited by a term of n, right? Because x is alive, y is alive, and we have got a vt that's restricted by n. So this becomes a continuous x y limited by n, right? So that's how now you have a formula, and if they give us the tables, we can easily evaluate this, right? So let's just do a question based on this, and I think that would give you a lot of clarity here, right? So this is the formula that we have to use, right? So whenever you have a confusion about these things, what formula to use, you can simply construct the integral and try to analyze the entire situation, and once you analyze this situation here, you can get your formula. Let's get to the question. Okay, so this is the example question that is given on page number 22, and it is based on the thing we just discussed. Okay, so Ralph and Betty are both aged 65 each, exact. Okay, their ages are 65, and upon Betty's death, Ralph will receive 20,000 per annum payable annually in advance. Okay, so he'll receive an amount of 20,000 that is payable not continuously but payable annually in advance upon Betty's death. So as soon as Betty is dead, okay, Betty dies, Ralph will receive amounts, Ralph will get paid, Ralph has to be alive, and he'll get it as long as Ralph is alive. Okay, so Ralph dies here, and I want payments to occur. Cool. So that's the idea behind it. And but the payments, there will be no payments on or beyond Ralph's 80th birthday. So see, they've induced a fixed time bound condition that 65, he's 65 right now. So at this fixed time, 15 years later, okay, 15 years is your foundation time, there would be no payments, right? Under any circumstance. Ralph's mortality follows PMA 92C20 and Betty's follows PFA 92C20. And the interest rate is 4%. Calculate the EPV of the benefits. Cool. So that is the idea behind this contract. Let's just see how we work this out. Okay. So since this is the same contract that we had discussed and there is a fixed term, you can as soon as you get the questions like these in the exam, you have to construct the integral, assuming that the payments are made continuously, and then you can apply them to advanced conditions, right? Since I've already derived it, I won't be deriving the thing again. You can go and check it how I did it. Okay, let me just do it for this one question. Let me derive it. Okay, so what are they wanting? They want that going from 0 to 15, right? 15 is my foundation time. I want the male age 65 to be alive at this time t. Okay, when will I be making the payment? I'll be making when the male is alive and the female is dead. So that is just TQ65F, right? She's dead, he's alive. And as long as both of these conditions are satisfied and t is less than 15, there would be a payment which would be discounted as VTDT, right? Now, in order to simplify this is simple. Going from 0 to 15, TP65M and 1 minus TP65F VTDT. And this, if you just expand it, it becomes going from 0 to 15 TP65M VT dt minus going from 0 to 15 TP65M TP65F, right, into VTDT. Cool. So this is what we have, and now I can just get you the answer. This says that this is just the annuity that is payable continuously for a life that is age 65 for the next 15 years, right? And this has to be obviously the male, and minus continuously 65 65 male, the female, and 15, right? So that's what I'm seeking here. And now since the payments are in advance, I will have to write the advance version, that is ADU M6515 minus ADU 6565 MF15. Okay, let's just write the answers. So this just becomes a ADU 65 minus obviously I'll have to apply the formula, so that's V15 into probability that a person age 65 male survives for 15 years into ADU 80. Okay, and minus this thing, it becomes let's just see. So this becomes ADU 65 65 minus V to the power of 15, obviously, into probability that 65 male survives for 15 years, then 15p 65 that the female survives for 15 years, obviously, and this multiplied by ADU 8080. Now these values are easy to pick up from your tables. Okay, so I'm gonna leave that job to you. Just put these values. Okay, I hope you get this. Okay, so just put the values, and you will get the answer as 0.5700, right? And if you don't get the values, just check the core reading. the same question is given there. And this the amount was 20,000 pounds, so that is multiplied by 20,000. So this just becomes 11401 pounds, right? So I'm ending the video with this particular part. Okay, I'm ending the video here because this was maybe too much for you to take and process. Just think on it and sleep on this basic idea. Okay, and next we do a lot of such integral based questions in order to derive these formulas. We will be deriving everything, and then this chapter would be over and we'll get to the revision notes. Okay, so let's just one more video, pretty sure about it.